Hello class. So this is the second video on section 4.9, talking about antiderivatives. So in the previous video, we defined what an antiderivative is, right? An antiderivative of a function little f is a function big F whose derivative equals little f, right? So we're going backwards. Instead of taking derivatives, we're trying to look for a function whose derivative equals little f. Right? And as mentioned, we also saw that if you find one antiderivative, then adding a constant gives you infinitely other, right? Infinitely many other antiderivatives, because when you take the derivative of a constant, you get 0. So adding a constant doesn't change the derivative. Okay. Now that was important in the previous video, because in fact, all antiderivatives of a function look like that. Okay. So what do I mean? Okay. Let f be an antiderivative of little f. So let big F be an antiderivative of little f on an interval I. Then all the antiderivatives of little f on I have the form big F plus c, where c is an arbitrary constant. Now that's really big, because what is that telling us? Right? So in the previous video, for example, we saw that if we start with f of x equals 1, right, then big F equals to x is an antiderivative, and so is any function that looks like x plus c. What is this theorem telling us? It's telling us that every antiderivative of 1 has this form. Okay? So every antiderivative of f of x equals 1 has the form x plus a constant. Now that's very powerful. And if you think about it, we know that there's, okay, so how many functions can we find whose derivative equals 1? Well, this is telling you all of those, infinitely many as they are, they all look like this, x plus a constant. Okay, so that's very powerful. And that's why in the previous video, I made a focus that once you find one antiderivative, you can find infinitely many by just adding a constant. This is going even further and saying all antiderivatives look like, well, just find one, specific one, and then add a constant. Okay? So again, very powerful. Now, why does this work? Well, I'm going to ask you to prove it in the homework, just as a bonus, but basically it hangs on the fact that if you have two functions who have the same derivative, they are the same or they differ by a constant. And we did that in I think either section 4.6 or 4.7. Right? We covered that theorem. Right? So you'll be able to see why it works. It's pretty easy to show, and I'll ask you to do it in the homework for an extra credit. Okay? But for now, just believe it that this is true. As crazy as it sounds, that all antiderivatives look like this, that's how it is. Okay, so let's do an example. Actually, two. So find all antiderivatives of g of x equals 11x to the 10th and h of x equals cosine of 4x. Okay. So by the previous theorem, if we want to find all antiderivatives, all of them, what do? First, find one antiderivative, any antiderivative, just one. So let me just write any to make it more clear. So find any antiderivative and then two, just add a constant. So find any antiderivative. Since we're starting with g of x, let's just call it big G. And then what else do we know? Well, all antiderivatives will look like so when they're asking you find all antiderivatives, really all you have to do is find one of them and then add a constant. Okay, so C here is an arbitrary constant. And all antiderivatives are going to look like that. Okay. So let's do this. Let's start with g of x. So we want a function big G such that the derivative of big G equals 11x to the 10th. Now here we can do the same process as we did in the last video. We know that if we have a polynomial of degree 11, its derivative is going to be a polynomial of degree 10. Okay? So it's logical to start with something that looks like a constant times x to the 11. Because again, once we take the derivative of this, the power of x is going to go down to 10, which is what we want, almost. Okay. So let's go ahead and find what the derivative of g is, as it is. Bring the 11, we have the extra c, x, and we subtract 1 from the exponent. So we're almost there. What does this say? Well, right now we have 11c times x to the 10. All we want is 11 times x to the 10. So we can just let c be equal to 1. And now we have the answer, right? Because what is an antiderivative? Well, if we let g of x be equal to x to the 11th, then we can check that its derivative is just 11x to the 10, which is what we wanted. Right? So g of x equals to x to the 11th is an antiderivative of, g of x equals 11x to the 10. Now we're not done, right? Again, this is just the first part, right? If we want to find all antiderivatives, you first find one specific one, which we found, right? So now if we want to find all antiderivatives, well, you just add a constant to this. So all antiderivatives of g of x equals 11x to the 10 have the form, well, g of x plus c, which is the same as x to the 11th plus c. And those are all the antiderivatives of g of x equals 11 times x to the 10. So really easy. Just find one specific antiderivative, whichever it is, and then add a constant. Okay. Now let's do the same thing with the other function. So the other function was h of x equals cosine of 4x. We want to find all antiderivatives. So let's first start with finding one specific one, right? When you want to find all of them, just find a specific one and then add c. Okay. So we want a function h of x such that the derivative of h equals cosine 4x. Well, we can do the same sort of analysis like that we did in the previous example, meaning that what function do we know whose derivative is cosine? Well, we know that the derivative of sine is cosine. Right? So it makes sense to try out something that looks like this. Some constant times sine of 4x. Again, because the derivative of sine is cosine. So it makes sense to try something like this. So if we have this, what would be the derivative of h? Well, by the chain rule, well, the c stays there, it's just a constant. And then by the chain rule, we just bring the 4 outside and we'll leave the inside the same. Right? So derivative of the outside, leave the inside the same, multiplied by the derivative of the inside, which is 4. Okay. Now, this almost looks like what we want. Right now we have c times 4 in front, but we want just 1, right? We want the derivative to be cosine of 4x. So what does that mean? Well, we can choose c to be equal to 1 over 4. And now that gives us the correct antiderivatives, because we can check that if we let h of x be equal to 1 over 4 sine of 4x, well, then what is its derivative? Again, the 1/4 stays outside. Take the derivative of the outside, leave the inside the same, multiply by the derivative of the inside. The 4 and 1/4 cancel. We're left with cosine of 4x. Right. So h of x equal to 1/4 sine 4x is an antiderivative of cosine 4x. Hence, to find all of them, we just add c. So all antiderivative of cosine 4x have the form, well, h of x plus c, which is the same as 1/4 sine 4x plus c, where c again is just any constant. Okay, and that's basically what you do. Want to find all antiderivatives of a function, find a specific one, and then just add c.